I'm sorry.
Okay. How are you guys doing?
Good.
How's the homework going? I like to hear any enthusiasm. I have enough scholarship from 4 to 6. Also, supposedly I'll have enough hours in the next Wednesday, but I'm pretty sure no one will be interested enough hours next Wednesday. So I'm changing my hours from next Wednesday to next Tuesday. Okay, so it's the day before the exam. It's the day before the exam. Does 4 to 6 work for you guys? What? Order? Oh, I can make it 4 to 6 on Monday. Yeah? Okay. So let's make it 4 to 6 on Monday.
So nothing is
Yeah, no. Just that's fine with me. Yeah. So on Monday, I'm just gonna talk about the homework and see if you guys have already any questions on the homework or any topic. So for all purposes, the content of the exam. Okay, I don't think it's really fair to demand you guys to learn something on Monday and question learn it on Wednesday. Some things they take a while to settle. Okay, so today we're going to continue talking about auction theory. I changed the example a little bit, so because some people complained that the range going from 0 to 20 and 20 beers was a bit confusing. So I'm going to do the same example as we had before, but I'm going to have the range of the valuations be from 0 to 10 and 20 liters. And then I'm going to see what is the optimal bidding function for what is the strategy that you should have for a second price auction. And then we're going to talk about the revenues that each of auction yields. And then we're going to talk a little bit about auctions in general. And then if I have time, I'm going to make some comments about this magic information, some general comments. Okay? Any questions? Okay, so the example that I had before is still the first price auction, but it's slightly modified. So, So 20 bidders and all the valuations, we don't know all the valuations, but the valuations we know that they come from a distribution that is uniform between 0 and 10. Okay? So And so every time we're doing something from the point of view of the bidder, the solution is going to be a function because he knows his own valuation. But if we do something from the point of view of the auctioneer, the guy selling the good, the solution will be a number because he does not know anyone's valuations. So we just look for the expected result. Okay? So we'd like to compute the bidding function, which is the rule that you're going to bid for something as a function of how much you like to bid. Okay, just in order. Okay, so basically what the person has to solve in this first price auction here problem is to find the bidding function that maximizes the following utility. Expected utility of I as a function of the valuation and the bidding. So what we have to do is to maximize pi, and we know that the expected utility function is going to be pi minus pi times the probability of winning okay. Differentiating this function here, we get that the first order condition for BI implies a VI minus VI and I did exactly this in the previous class, so I'm not going to spend too much time doing this again. But the only issue is now it's a little bit different. Distribution is a uniform between 0 and 10. And I'd like to see what's the probability of winning. Now this is a differential equation, so in order to simplify, I'm going to let you guys assume BI is equal to gamma BI. I changed gamma instead of alpha so people don't get confused with my true and my gamma look alike, so like this is a little bit better. And now we can see what is the probability of winning this auction if you bid BI. Can you see from there? Okay, good. Probability of winning with BI is equal to the probability that BI is bigger than B1, which BI is bigger than B2. And BI is bigger than B20. Now using this assumption here that we have that they all have the same leading function, we get this. Yes, Kate.
Why did we set it equal for some condition equal to the probability of getting here?
Let's differentiate this function here. Okay? What do we get? You see now? We make this equal to 0, and we flow to the other side, and we're going to get this. In some sense, it's good that you have something that's positive and something that is negative there, because it depicts that there is a trade-off. The trade-off is, if I increase BI, it increases my probability of winning, and that's a good thing. But also increases how much I pay if I win, and it's a bad thing. Yes, Sasha.
Why is it that when you plugged in the assumption, why is it alpha BI?
Yeah.
Is it BI?
Yeah, it's wrong here. Thank you. Oh no, it's good. What did you say? No, it's 20. This here is 20. It's still 20. Because there are 20 years on here. Okay. Alpha BI is bigger than alpha B. And now it's right. And then I can, this gamma for God's sake. And now I can cancel all the gammas there. And this is equal to probability the VI is bigger than V1, and the VI is bigger than V20. Since those are independent, since they are independent random variables, we know VI is a number. Okay. For us, we're going to know exactly what it is. It's your own valuation. You know how much value the good is going to be sold. So it's a number for you. V1, V2, V20 are random variables. You don't know what they are. And they are independent random variables by assumption. So we can break this probability between products of probabilities. You can also tell it change the sign of the inequality there, so it gets a little bit easy to understand it as a CDF or as a probability. Okay, this is a random variable here has to be smaller than a specific value. But now, okay, since they are all identically distributed, this is equal simply to the probability that V1 is smaller than VI. Elevate the 2. How many times you have up here? 19 times. Because there are 19 inequalities here. I just have to be bigger than anyone else. I don't have to be bigger than myself because that's impossible. Okay. So far, this is exactly what we've done in the previous example. What does it change now? What is this probability here? Can anyone help? Can anyone help me? what is this probability that this random variable v1, who has a distribution that is a uniform between 0 and 10, is smaller than a specific value vi. Vi over 10. Thank you. Okay, and this here is independence. This here is the same distribution. And this here is because it's a uniform between 0 and 10. But now we would like to have this as a function of bi. Because if you look there on the other side, you're trying to see the probability of winning as a function of our own b. So we can use again the assumption that we used here before to get back to vi here. This is because we get this. Okay, so now we solve for the probability of winning as a function of our own bidding. Now all I have to do is differentiate this function and plug it back in there. Okay, so fine, this is equal to the probability of win with bi. Well, the probability prime of win with vi has to be equal to 19 vi elevated to 18 times 1 over 10 gamma elevated to 19. And now I'm just going to rewrite this first order condition here. Everything vi, probability of winning, and prime, the probability of winning, everything is just in terms of bi and gamma. Okay. Has to be equal to this is the first order condition that we had before. Yes, Twinkle.
How'd you get the v sub I over 10?
Oh, this is what a uniform says.
Oh,
This is what is the conditional distribution function of a uniform. It's kind of easy. If you think about the uniform, everything is spread equally. So let's say it's a uniform between 0 and 10. What is the probability that this random variable is more than 7?
So it was that?
Let's say we have a uniform between 0 and 10. This random variable, something that we don't know what it's going to be, has this distribution which is a uniform between 0 and 10. What is the probability that it's more than 7? 7 divided by 10, 70%. Okay? This probability is really nice. If this was a normal distribution constraint to this interval, this wouldn't be true. Okay? But because it's a uniform, it is. It's just like it's like the area. It's always the area, but it's area over time. We don't have to integrate a function. Okay, so this is what I got this here. So now we're doing some algebra here. get this. Now we cancel this again. Okay, okay. First, there's a. Which letter is this? It's a very simple question. What? M of Mary? Yeah, I have problems. Like in Brazil, I was taught this is this, and this is this. So I think there's no M in the problem. It's always N. I never put M's in problems. So just some people, I heard some people coming to me and say, oh, what is M? M? And I said, no, there's no M. It's always N. Sorry if you're confused with that. So this is like the general rule would be. It's very useful. It says that if you were to, if you're going to bid something, and you know there are n bidders out there, it's a first price auction, and if you value $4 the good, you should bid. Well, there are 20 guys there. 4 divided by 20, 20 cents times 19 should be 380. Okay, with this, now with this rule here, we can calculate what is the expected revenue of the auctioneer. So the bidding function in the end is 19 pi divided by 20. And this is the solution. This other specific number is a function. Okay. Yes?
When we solve for it, do we have to do it this long way, or can we just use a shortcut?
Depends on the question. It's like the question is like solve for this here.
When we do it the long way?
Yeah. If the question is like find something else. So the expected revenue in this case here is going to be the expected maximum and now we don't have 19 here, we have 20 possible bids because he doesn't have his as his own reference, which is equal what is expected maximum of 20 bits? I'm sorry, what's expected maximum of 20 valuations? I gave you guys a formula in the previous class to figure out this. Right? It's a property of this uniform distribution. I want you guys to go back there and help me figure it out. Yes. Okay. And what is A in this case? So this is going to be, and look, I promise you guys, I don't want people memorizing stupid stuff. So if this is going to be the final exam, you're going to have, I'm going to put this in the formula, okay? The formula to solve for this. So you don't have to memorize formulas for it. So this is going to be 10, right? Times 20 over 21, because we're looking for the highest possible, right? Yes, Lydia.
Where did you get the alpha?
Oh, we solved for the alpha here. Oh, it's gamma. So, hope now it's clear. This is like, okay, do you understand what this is? What he's going to get, what the auctioneer gets, is the highest possible bid, right, of them all. And the highest possible bid is just like the highest possible gamma times the valuation. So gamma king comes out of the maximum of expected value, so it's just gamma times the expected maximum of them all.
How is it different than what we did last time?
It's not exactly the same.
So,
I'm just going there again for different examples, and we're going to do the others. It's pretty much the same. But what number do you get here? Can you guys help me figure it out? This is 19 divided by 20 times 10 times 20 divided by 21. So this is equal to 190 divided by 21, which is, can you help me here? Okay. It's approximately 9. Okay, so this is the expected revenue of the first price auction for good. Now I'm going to talk about the second price auction. Any questions here so far? This was exactly where we finished the previous class. So, let's think about the second price auction. And I brought a new good here so we can serve as auction today. It's some snacks that I have back there. It's like energy mix. I want you guys to look at this and think how much the maximum that you'll be willing to pay for this. Just think in your head, if you can, write down a piece of paper. They sell there, pretty much everywhere, so you can find this. And let's figure out, now that you know how much you value this, let's figure out a bidding strategy for you guys in the second price auction. I'm going to write down here. There's no way this is going to stay stuck here. I'm going to write down here what the rules of the second price auction, and we're going to try to figure out what is the best thing to do. Okay, but before you guys know that this asking for the second price auction is equivalent to asking for it's the same problem as asking for ascending auction, right? Well, because the idea is that if this is the second price auction, I could do exactly the same thing as going up of 20, 30, 40 cents. And the person who wins is the person who has the highest valuation, but it pays when the person before that gets halted. Do you remember how the ascending price auction works? No, it's not the rule, but the rule is like this. If I tell you all guys to raise your hand and to keep it standing up and keep your hands raised for the value that you're willing to pay, and people start lowering down their hands as they don't want to pay anymore, the person who wins the good is going to be the person who values this the most. But the person is going to pay what the second one, the person with the second highest valuation, is willing to pay. Let's do this again, so you guys can figure it out. Write down on a piece of paper how much you're willing to pay for this. Like everyone writes down on a piece of paper how much you're willing to pay. The maximum that you'll be willing to pay. Your own valuation. It's not necessarily when you have to lower your hand. Just think, I don't know, I like it a lot, $2.50. I don't like it so much, $1. Just write down the maximum that you're willing to pay. Has everyone done this? Okay. We're going to know a little bit more about the serving size, 28 grams, 3.5 portions per package. Okay, and I'm going to ask you guys all to raise your hand again. Everyone raise your hand. I'm going to start the auction again. If you don't want to pay this price anymore, you lower your hand. Okay? 10 cents, 20 cents, 30 cents, 40 cents, 50 cents, 60 cents, 70, 80, 90, $1, 110, 120, 130, 140, 150, 160, 170, 180, 190, $2, 210, 220, 230, 240, 250. So right there, guys, we go for 250. Notice one thing. So you can get here and write this. And let's try to solve for the optimal bidding strategy. What's your name again? Leon. Leon was the one who lowered your hand just before Hadria. Okay? And let's solve for what's the optimal bidding strategy for this auction, which is exactly the same as the second price auction. I'm going to show you guys, give you some tuition behind. Any question?
So I know I get what you're saying. So it's, by second price you mean that like Adia could have had like a higher valuation of that.
Yeah, she might like $10.
She never had to like
She never had to say it.
Right, but how do you know that wasn't actually her highest bid?
Because when I said that he lowered her hand and she didn't, so I assume it's bigger or equal to 250, her highest possible valuation. Maybe it's exactly.
It could be equal to as well. Right?
It could, but it's just like a problem of continuity. I agree with you. There's like usually it's exactly. You have it right. I'm going by 10 cents and by 10 cents, and maybe you're gonna run into problems in there. Usually it's equivalent if I have like this kind of clock of time that goes moving, and then it continues the money, and then you wouldn't have the problem of exactly equal. But all I know is that it's bigger or equal to 50. Maybe it was exactly 50. Okay, so second price auction. So, So the winner gets the good and pays the second highest bid, and the losers pay nothing. So the expected utility that you get I'm going to define this other object here. Is going to be called the B upper bar, which is equal to the maximum bid of everyone else but Q. Okay? So the utility that you get is your valuation minus the maximum bid of everyone else but you, if the I is bigger than the bid, the maximum bid of everyone else, bigger or equal. And 0 otherwise. So now I want you guys to think about it for a second, to remember when we auctioned this. Remember the number that you wrote in the paper before, which depict your valuation of this high energy mix. And now remember the moment that you lower your hand. Ruhi? Did I say right?
Yeah.
Ruhi, do you remember the number that you said was evaluation?
Mine?
Yeah. You don't have to tell, don't tell me. Do you remember the moment that you lower your hand? At 60. Okay. If it was 51, would you have lowered your hand at 51? Would you be willing to pay more? If you think about it introspectively, you probably should have lowered your hand exactly when you reach the point that you wouldn't be willing to pay for that anymore. Right? If you value this $1, I said $1, yeah, I would still pay $1, 110 no. Because when you reach 110, there is a probability that I'm going to win this, but I don't want to win this and pay 110. I would pay the maximum possible of $1. Basically what we're saying, this, and this should be what everyone should be doing, or something very similar to this, but for these questions of 50 or 60, 51 or something, but it should exactly reach the point that is your maximum possible valuation, you should lower your hand. Say, I don't pay for this anymore. What I'm saying here, in game theory language, is that to beat your own valuation is a dominant strategy. If I ask you this, how much you want to pay in this auction, you tell me exactly how much you value it. If you guys probably look back to your paper and remember the time when you lower your hand, you probably lower your hand exactly when the auction got to the point there was your valuation. And this is a proposition, and I'm going to prove here now. And it's kind of interesting to think how to prove it. Let me write the proposition here somewhere. Yes, I did. B bar is the maximum bid. You are here, and there is like everyone else bid. It's the maximum bid of everyone else but you. Okay, if you look at everyone else bids, and if there would be a B bar, would be the maximum of everyone else but you. And if I look at my bid, I would find the maximum of everyone else bid but me.
So it's the third price.
No,
Just like,
it's a second.
The third. Well, the winning bid was the second price, right?
Yes.
So the maximum for that would be third.
No.
So that this guy's bid,
Yes, and he was the second highest.
but the first highest did never got it. Isn't that the whole point?
I'm not sure I understand.
The highest bid, like, was never disclosed because of the way that.
Well, yes, but I said that this auction is isomorphic. It's not exactly the same auction as the ascending auction. The second price auction will be something like this. Just give me, guys, your bids in a piece of paper, and the winner is going to pay the second highest. And what I'm trying to say is that what you are going to bid, what you should bid, is your own valuation. So in this second price auction, I would get Hadia and his bid, and I would say, oh, Hadia has the highest one, she wins the good, and she pays his bid. Okay? They are equivalent, like modeling them is the same, but they're not exactly the same. So like taking time to appreciate the beauty and the generality of this result. I did not say for n bidders, I did not say because it was a uniform distribution. It was very general, like second price auction, bid your own valuation. Let's prove this, because this is an interesting proof. So, the proof we should do it by case, and show that every possible case, every possible combination is better off to bid your own valuation than to bid something else.
but isn't this the case in all the auctions? Even in first price auction?
No.
No?
Well, in first price auction, the bidding function is way up here. You don't bid VI. You bid 19 divided by 20 VI. You bid less, then you value the good. So, yes, Matt.
The first auction shows your utility was measured by your valuation minus your bid, right?
Yes.
And in this case, you're saying in this case, so in the first case you want to bid less than valuation. In this case, you want to bid exactly the valuation.
Yes.
But according to your like piecewise, it's kind of yeah. So that says your valuation minus your bid.
No, it says evaluation minus the bid of the maximum bid of everyone else but you. Okay? This is not BI, this is B bar, which is this guy here. It's a good point. So let's prove that the best thing that you can do, let's go case by case and see that in every possible case, you cannot do better than bidding your own valuation. So the first possible case is that you value something that is that you are the guy with the highest possible valuation. You are the guy who is in the triathlon team, and you really need a high energy mix, so you really value this. You're going to run this afternoon, so it's important for you to have this around. Okay? So in this case, your valuation is bigger than the bid of the second highest person. Okay? So what utility do you get by bidding your own valuation? if you're the guy with the highest possible valuation and you bid your own valuation, what do you get? You're going to win the auction. Right? You're the guy who values the high energy mix more than everyone else. So if you bid and you value more than the maximum bid out there. So if you bid your own valuation, your utility is going to be you're going to get the good and you're going to have to pay the second highest one. So in order to make a formal proof, we should look at all the other possible deviations, all the other possible things that you can do, and see if you can improve in any case. This is like a domino strategy case. So, okay, so if I'm the guy who values the good the most, and I bid my own valuation, my VI equals to VI. No, wait, this is kind of wrong. It's just a little bit. Not nice. This is how I value the good, this is how I bid. I will get a positive utility out of this auction. What if I lie up? If I lie and say that I value, I am in Hadia's point of view, I value this, I don't know how much he values. All I know is there's more than 250. But let's say she valued $3 this, and she lies and say, oh, I actually valued $5. What is going to happen? So, if anyone? Are we together? We are under the case. This is the first case. That you are the person who values the good the most. Okay? If you bid your own valuation, you're going to win the good, and you're going to pay the second highest. Right? So your utility is going to be your own bid, your own valuation minus the second highest bid.
So you're paying the first highest bid. Because you are the one who values the good the most, and you're bidding the valuation.
Yes.
So that would be the first highest bid.
I'm paying the second highest bid, the one who values the most, but yourself. I think you're confused here with B bar.
Yeah. I don't see the distinction between the second and first highest bid. Because you're saying that the whole thing is that, like, the point of this sort of auction is that the first bid never gets to come out, right?
No, it's not that. It gets to come out. Look, Hadia, how much did you have there as your valuation? 3.
Okay, if she bid $3, that would be the first highest bid.
Yes, and she would pay 250.
Right, but if she were to, that would be the first highest bid.
If she wrote 250,
If she wrote $3.
that would be the highest bid,
Right.
and she would pay 250.
But
I'm not sure I understand what this.
it's okay.
So she has 3 as valuation, and he has 250 as
But you're
valuation.
saying you're bidding your valuation.
Trying to show that to bid your own valuation is the best thing that you can do. Okay? I said that in this case here, if Hadia bids her own valuation, she gets $3 and she pays $250. Okay? If she bids something higher, what's going to happen? She bids $350. She still gets the good, and she still only pays $250. So it doesn't change. So she still is going to get the same thing. just think, okay, in our example, sorry, I'm using your name. B bar is equal. Yes, Sasha.
Why? Okay, so I understand, yeah, B bar, I understand all that. Why is it if BI is greater than BI? What is BI? BI is what you actually bet?
It's what should be.
Oh, it's for good, okay.
If she bids higher than her